Woohoo! Welcome back. Today we're going to be doing part 2 of our video on average velocity and instantaneous velocity of a rock that we threw off of the surface of Mars. And so I'll remind you, here's our original problem right here, and a rock was thrown and we've got a height function. And so let me go ahead and copy that height function down. So we've got our height function. H at time t is 10t minus 1.86 t squared. And again, let me remind you that since we're on Mars, the acceleration that this rock experiences due to gravity is smaller because Mars is smaller, so there's less attraction. The bigger you are, the harder you pull, or something like that. So we're going to look at, instead of the average velocity, the instantaneous velocity, which is kind of somewhat cheating and peeking into the next section. But I figured, hey, let's do that. It'll be fun, super fun. So what is the difference between average velocity and instantaneous velocity? Well, if we look at the graph of height over time, so if this is time going this way, and this is the height, then basically we know that when we throw rocks up in the air, they go up, then there's a moment where they think about their life choices, and then they decide that they'd really rather be home again, and they come back. And if I had been more of a professional, this would be more symmetric. Let's just pretend it's symmetric. And I'm going to say my magic spell of NTS, not to scale, and that fixes everything. So we've got this graph, and if I want to know the average velocity between these 2 points, the average velocity is the slope of the secant. And so between these 2 points, this slope means basically between here and here, the velocity was the slope, so it's positive. It was mostly going up. Now, is it going up the entire time? No, there's actually a little bit where it get to the top and it headed back down, so it would have a negative velocity. But because this is average, we don't get that level of detail. So the question then becomes, what is the instantaneous velocity? And the instantaneous velocity, and let's say, let's call this point t equals a, because that's what we're going to be using in this problem. The instantaneous velocity, and here I'm going to have to draw the tangent line. The tangent lines are not a forte of mine, but I'm going to give it the old college try. The tangent line is the one that just skims along the curve at that point, and the tangent line is going to give us the instantaneous. So the tangent line slope, the slope of this is going to give us the instantaneous velocity. These words all sound so fancy. You can impress people. Oh yes, we're studying the instantaneous velocity in class today. So, impress your friends. You'll get very popular. Everyone loves math. It's just the best. So you can see that actually at this point, when we look at the tangent line, it is more accurately representing what's happening at this point, which is it got to its top point, that vertex, and it's heading back down, which is what we expect rocks to do. As long as you're not shooting them using an actual rocket that's going to keep propelling it up into space, we expect that rocks will go up and then they will come down. And at this point in this graph, the way I drew it, t equals a is the point where it's already starting to head down. So the velocity is negative, even though the average velocity between these 2 points is positive. Average velocity will give us some information, but not a lot of precision. Instantaneous velocity will give us the precision of that point, but it doesn't really tell us about anything else. So it's two different measures. But the question is, how do we get to the instantaneous velocity? And that's where we're going to do the preview. Woohoo! I know, this is very exciting. So the instantaneous velocity is going to be what happens when we look at a bunch of slopes like we did in class. Sorry, you can't see that. A bunch of slopes. I'm drawing little fake lines there. We're going to look at a bunch of slopes, and then we're going to look at what happens when effectively these 2 points get closer and closer. And we can come from either side. So we could come from the right or we could come from the left. And you could see that if I drew a lot of lines getting closer and closer, I would eventually get to this line. Same thing over here. If I did lots of little points like this and like this, the closer I got to that point, the closer I would get to this slope. And so that's what we're going to set up. And now this is dead mathematicians made this decision. So you just got to take it on faith that this is the way that it is done. The way we're going to look at this is we're going to look at t, that should be rounded, equals a to t equals a plus h. We use h as that little bit of extra. And the thing is h can be on either side. Over here, if this is a, h would be negative. And over here, if I looked at these secants as h got closer and closer to 0 as my extra point got closer and closer to a, that would come in for the right side. So we're looking at limits from either side. And I'm going to look at what happens when t goes from a to a plus h. And so I've got to do some algebra. H of a, is 10a minus 1.86 a squared. So far, so good. Now, h of a plus h is going to require some remembering of formulas. Because we're going to have to multiply a plus h, the quantity squared. This is going to be 10 comes through, right? Multiplies times the a and the h, 10a plus 10h. And then this is going to be minus 1.86 times, and I'm just going to multiply this out. I happen to have this memorized. You can either use the formula for the square of a binomial, or FOIL. And we get a squared plus 2ah plus h squared right there. There. FOIL, or the formula for the square of a binomial. And then I have to multiply. And I realize this is not going to be anyone's favorite thing. So, but maybe it is. Maybe it's your favorite thing. That would be amazing. 1.86 a squared minus 3.72 ah minus 1.86 h squared. Okay, so that's h of a plus h. Notice that's why I have a capital H for our function, because we're going to have a lowercase h. Totally different h's. And now remember, we want the difference quotient. The difference quotient is what happens when we take the point at a plus h and we compare that to the point of a. So we're still finding an average velocity. But what ends up happening is I can simplify a few things and I end up with just h in the denominator. Woohoo. Okay, you guys ready? Dun 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 dun. Doo doo doo. Doo doo doo. Okay. So, where's the paper? There's the paper. You guys ready? This is going to be h of a plus h minus h of a all over h. And again, as I mentioned in class, sometimes people turn their paper sideways to give themselves more room. I'm gonna do this just as it is because I'm feeling it today. Okay, I've got 10a plus 10h minus 1.86a squared. I shouldn't have been feeling it. I don't think I have room. Minus 3.72ah minus 1.86h squared minus, oh no, minus 10a minus 1.86a squared. And this is all over h. Can you guys see that whole thing? Not quite. Let me move this sideways. There we go. So this is the fancy one with a plus h. This is just the plain version with just the a. Okay, let me try to give myself more room. I get 10a plus 10h minus 1.86a squared minus 3.72ah minus 1.86h squared. Then subtracting, so I'm going to change the signs. Minus 10a plus 1.86a squared. Did I make it? Yes! Just barely, all over h. Now, when we do this, notice that I've promised you anything that doesn't have an h in it will cancel itself out. So the 10a right there and the minus 10a cancel out. And the minus 1.86a squared and the plus 1.86a squared, they also cancel out. So then what I have is 10h minus 3.72ah minus 1.86h squared all over h. Now, where we're going to go from here is, remember, if I'm going to cancel this h, that's when I want to factor out here. And no matter what else is factorable, don't factor anything else out, just the h. So I'm going to factor out an h. That leaves me with 10 from the 10h minus 3.72a because I factor out the h and minus 1.86h because I take one of the h's. And then I cancel the h's and I get 10 minus 3.72a minus 1.86h. That's very exciting. I can tell you are all like, wow, that's just amazing. So what does this mean? That is basically, this is the average. Can you see that? Let's scoot you up a little bit. The average velocity of the rock between A and A plus H, right? Between those times. So what do we want to do? Do we want a big old secant? No. What we want is we want to take the distance between A and A plus H and shrink it down. Get it as close as we possibly can. So what's the difference between A and A plus H is H. So let's shrink H down. So that means I'm going to move the points closer together. So I'm actually going to do something that I said we weren't supposed to do, right? I said, let's not let h be 0, because if we let h be 0, then this is a problem, because we got h in the denominator. But we carefully canceled out the h's, so we can actually calculate the limit. So the limit as h approaches 0 of capital H, A plus H minus capital H of A all over H is the limit as h approaches 0 of this thing up there, 10 minus 3.72a minus 1.86h. Well, if I take the limit as h approaches 0, that just means this term cancels out, right? We get 10 minus 3.72a minus 1.86 times 0, which means, dum, dum, dum. Ooh, that was exciting. I almost knocked over my coffee. You should drink your coffee because when you knock it over, the caffeine doesn't help at all. So that's going to be 10 minus 3.72a. And this is the instantaneous velocity at t equals a. Oops, you can't see that at all. Let me scooch this up. There we go. Magical writing that you didn't see happening. So what does that mean? Well, that means that instead of looking at the average velocity, which has us look at two different points, and then we look at the slope of each of those secants. Instead, what we can do is we can look at the slope of the tangent line. So this is the slope, can you see that? Yes, of the tangent line at t equals a. So in other words, we can look at the actual, that line that just involves 1 point. So we're using limits so that instead of having to look at 2 points, we can look at just one. We let the 2 points squoosh together. It's kind of trickery, but it's kind of magical. And this is literally what calculus is. Woohoo, we did calculus! Yay! So you can tell everyone you did calculus today. Do the calculus dance. I don't know what the calculus dance is. You guys can probably come up with a cool calculus dance. But I'm going to leave you here. And in the next video, we're literally going to come back to Earth, except we're going to come back to Mars and see what happens when that rock finally hits the ground, and talk a little bit about terminal velocity, a very small bit. And until then, I hope you have a great day. Take care of yourself. Keep in mind, this is some of the most complicated and confusing math there is. I mean, this is calculus. This is the big one that people talk about. So be gentle with yourself. Ask lots of questions. Reach out to tutors. Talk to people on the street. Ask your family. Have a big old calculus party so you guys can all wrap your heads around what's going on. You can dress up as a tangent line for Halloween. How cool would that be? But otherwise, be really gentle with yourselves. Maybe go out, touch a little grass, look at the sun. If there's sun today, if it's raining, it'll be harder to see the sun and you might get wet, but, maybe go out and just get a little bit of oxygen that didn't get piped in through tubes. And honestly, just woohoo and math on. You did it. We did it. We did it. Woohoo.